These are the notes for LT4 in the sound and wave unit. Target says, I can analyze how a forced vibration at an object's natural frequency causes resonance. As you can see, there's three concepts that we focus in on: forced vibration, natural frequency, and resonance. All right, we're going to apply it, obviously, to some real-life situations here. So I'm going to start out with just the good old definition of forced vibration. This is when you make something vibrate at its natural frequency. Okay, you make something vibrate at its natural frequency. I would like to say that you just force it to vibrate at its natural frequency, but everybody knows that if you're going to define something, you should not use any version of that word in the definition. So think of it as if you knock on a door. Your knuckles hit the door, and they force it to vibrate at that door's natural frequency. You know if somebody's knocking on the door. You don't have to look. We learn to recognize that sound. If somebody drops their cell phone on the floor, like we all cringe right along with them, we know the sound a cell phone makes when it hits the floor because that cell phone has a natural frequency. If you're in class, I randomly drop an aluminum pop can and then a plastic pop bottle. We know the difference. We know they sound different. And those differences are what account for the natural frequency of something. So if we skip a little bit of space here, different materials would give something a different natural frequency. So whatever the material is made out of, right, that could determine the frequency something vibrates at. The shape, okay, the shape of something, the size of it. I tried to self-teach myself to play the guitar, and that was an incredible fail. But regardless, I know that depending on the size of the string, that affects the pitch of the sound. So the thinner strings, they vibrate faster, higher frequency, therefore they create a higher pitch sound. All right, that would be an example of that. And the third one is elasticity. Things that aren't very elastic don't make much of a noise if you drop them. If you drop I don't really want to do it, like a tape dispenser or something like that. I'm looking around here. Something that doesn't have a lot of give to it, it doesn't make much noise due to this lack of elasticity, but it still would have a natural frequency. It's just not going to be much for amplitude. So, natural frequency defined. Natural frequency, and we're going to abbreviate it NF so we don't have to write it out a lot. It is the rate at which, so we can't say frequency, that would be cheating here, the rate at which an object vibrates. All right, the rate at which an object vibrates. So let's think about it in terms of knocking on the door. The forced vibration is the knuckles force the door to vibrate. Now, the noise, the sound the door makes, that is based on that. Based on, is it a wood door? Is it a steel door? Big door, skinny door? Is it very elastic? Okay, is the material elastic? Is it glass versus steel? It's going to be very different. Okay, so the knuckle part, that's the forced vibration, and that forced vibration causes it to vibrate. Once it vibrates at this natural frequency, which is determined by all of these things. Now, you should be still thinking, why do I care? All right? This has some huge implications in life. Because of this natural frequency, you can cause things to resonate. So the next word is resonance. Resonance is an increase in the amplitude. So go ahead and say amp. Increase in the amplitude. Remember, amplitude is energy of a wave due to forcing an object to vibrate at its natural frequency. And you usually have to sustain that, so it's over a long period of time. So we're going to talk about a non-scientific example first to hopefully help this make sense. I think we have all been on a swing set in our childhood. Perhaps at lunch, I don't know. Maybe you still like to swing. So think about a swing set. I was an only child. Lonely life, all right? So you can't always get mom, dad, or grandma, grandpa, family dog, whoever to come push you. So you got to swing. You got to get yourself going on your own. Real early on, we learn to pump our legs, right? We know as we go up the backswing, so you go back, that you pull your legs in, and then at the top of that backswing, you kick your legs out, right? That makes us go higher, and we learn to go in sync with it. We know to match what's happening. I don't think any of us are nerdy enough to know, ooh, I must match the natural frequency of the set in order to increase the amplitude. Like, we don't think about that. We just know what to do. But this is perfect, because if you pump your legs, that is the forced vibration. So here, let's call this FV, all right? That's the forced vibration. You are going to match the natural frequency of the swing set. As you do this, you swing higher. That swinging higher part is the increased amplitude. That right here, this is the resonance. Okay, that is the resonance. So you learn, all right, the rate at which the swing is going back and forth, I pump my legs in sync. You pumping your legs is a forced vibration. You have matched the natural frequency. You're going at the same rate, and you keep going higher and higher and higher until you can't do it anymore, right? That going higher and higher, that is resonance. So hopefully that's a simple example, because we're going to apply that to a couple things. And the first one, you're going to want to pause me, because this is going to make very little sense if you don't watch the video. On Moodle, there is a link to the Tacoma Bridge. And the Tacoma Bridge, it's going to look very similar to the Mackinac Bridge. There's not as many lanes, so it's more narrow, not as long, but it's a cable-stayed bridge, just like the Mackinac Bridge is. And they did not know that this bridge would crumble due to the fact that their composition, the shape of their bridge that they built, the materials used, was within the natural frequency range of the wind. All right? And so what happened that day is they received a 42-mile-an-hour wind. When I did a quick Google, like the Mackinac Bridge will close right around 65-mile-an-hour winds, and that has nothing to do with natural frequency for the Mackinac Bridge. That's the speed at which there's a high risk for cars to blow off the side. So we shut down the Mackinac Bridge, not because of natural frequency. We fixed this problem, but because of cars potentially blowing off. This is not enough to blow a car off a bridge. All right, so 42 miles an hour. What happened is because of the material, shape, elasticity of the things they used in this bridge, it matched the bridge's natural frequency. So again, watch the video. This is not the time to skip any steps here. And you see the bridge twist. It starts just a little twist, and then it gets bigger and bigger and bigger. So if you match that natural frequency of the bridge and sustain it, you start to see the bridge resonate. So you see it twist and twist and twist. And it's like an hour of this twisting before the bridge actually breaks, which blows my little mind, like the fact that it could withstand this. But we've learned from this. Engineers now know we want to make sure natural frequencies are nowhere near anything that could be done by wind or big semi-trucks going over it and vibrating it. Like, they make sure that this is not going to happen again. I'm not a military expert, but I've read that in the military, let's say that we have soldiers off to a war and we're in a less developed country where maybe the bridges aren't very fancy. When you think about a troop or a platoon going through, we've watched a lot of movies. We know usually they're in step, right? They're synchronized as they march. They will break step going across those bridges. They do not want to cause a repetitive force vibration that would match the natural frequency of that would cause the footbridge to collapse. Historically speaking, I'm not a history buff, but I've read there have been situations where we've lost soldiers because they kept in step, so they're all synchronized. It happened to match the natural frequency of the bridge, and down she goes. All right. So there's one example. Another one, also on Moodle, shattering glass. All right. It is entirely possible if you have a pure glass. The glass they use in the video is a wine glass, but any type of glass that is very pure in composition and pitch. So it probably can't be a on-sale special from Dollar General. Not that that's bad, but it probably can't be that type of glass. It has to be something that vibrates at a very specific frequency. So the glass in the video that you should watch happens to vibrate at 556 hertz. So what this person does is he sings, essentially. It sounds more like a yell, but he makes this high-pitched noise. So his sound wave, his name is Jamie Vandera, is 556 hertz. Again, watch this video. It shows a Mythbusters clip. He was on Mythbusters doing this. It's pretty cool. That perfectly matched the natural frequency of the glass. So it was also 556 hertz. It doesn't mean all glasses are 556 hertz. Okay, you would have to figure out what is the natural frequency of that glass. You put your finger on, does it sound high, low, do a quick little flick on it. And then if you can sustain it. So I can't sing. I sure do try a lot, much to my family's dismay. But I don't sing very well, so I could not keep a pure pitch over a long period of time. But if you've got some skills, you could sing at this glass, match that natural frequency. The decibel level is not that important. It's the frequency that matters, and you could cause that glass to shatter. If you can sustain it, go to YouTube even. Just type in sound wave resonance. All kinds of people like to put themselves up on YouTube to demonstrate this. All right, it's pretty cool to see. So you would cause it to resonate, which is the increase in amplitude until it breaks. All right, so not saying that's a super useful application, and this is obviously, it's useful that we know what happens, but it's useful that we can avoid it. If you are in band, and I told you I tried to self-teach the guitar. It was a horrible, horrible idea. But if you're in band, musical instruments work on this idea of resonance. Whether it's a string instrument, I think they're called wind instruments, like flutes, perhaps. I don't know. I could be wrong. But you get vibrating air columns at a specific natural frequency that resonate to produce the sound that you're looking for. All right, so again, please don't skip the videos. They're fun. They're not boring science videos. So don't skip them. And that is it for that one. Good luck.